Hello everyone, my name is Zefania Bramanta Saputra. My student ID is 136-18104. Today, I'm going to talk about AE3201 course, Astronautics. It is going to be about my third assignment, reconstruction of an interplanetary space mission. The interplanetary space mission that I choose is Venus Climate Orbiter, Akatsuki. Its goal is to unravel the mysteries of Venus with an emphasis on atmospheric dynamics. It is operated by JAXA, the Japan Aerospace Exploration Agency. With 6 observational devices, the orbiter will investigate the presence of volcanic activity and lightning as well as the composition and flow of Venus' atmosphere. Akatsuki was launched on 20 May 2010 at 21:58:22 UTC and attempt its insertion to Venus orbit on 6 December 2010, but unfortunately it failed. After lots of recovery efforts, Akatsuki successfully performed Venus orbit insertion on 7 December 2015. At the moment, the status is successful in progress. This is the logo of Akatsuki mission, where on the bottom left, we have the illustration of Akatsuki, where behind it is the Venus planet. The content of this presentation will consist of 6 big parts. The first one is launch site and launch vehicle. The second one is parking orbit and parameters. The third one is hyperbolic escape trajectory. The fourth one is heliocentric trajectory. The fifth is hyperbolic arrival trajectory. And the sixth one is the comparison between the reference data and the recalculated data. On this presentation, the analysis of spacecraft mission trajectory will be emphasized. The first one, launch site and launch vehicle. The launch site of Akatsuki is located on Tanegashima Space Center, specifically in Yoshinobu Launch Complex. It is located at 30 degrees 24 minutes 8 seconds north, 130 degrees 58 minutes 30 seconds east. It has short name of LCY and it is operated by JAXA. The launch vehicle is manufactured by NEC Space Technology. It has launch mass of 517.6 kg with dry mass of 330 kg. The propellant is liquid monopropellant hydrazine, which is N2H4, with specific impulse of 220 seconds, and it has propellant mass of 196.3 kg. It is launched on 20 May 2010 at 21:58:22 UTC. The spacecraft is attached to H2A202 rocket. The core stage. It has launch mass of 114,000 kg with fuel mass of 102,800 kg. The specific impulse is 349 seconds. The solid rocket boosters. The launch mass is 2 times 76,400 kg with fuel mass of 2 times 65,400 kg with specific impulse of 280 seconds. While the second stage has launch mass of 18,900 kg, which is assumed, with fuel mass of 16,600 kg. It has specific impulse of 447 seconds. The following are the pictures and the illustration of the rocket H2A AE3202. Moving on to the second part, which is the parking orbit and the parameters. The parking orbit is assumed to be a circular orbit with altitude of 300 km above the Earth. On the right side, we have the table consists of parameters that will be used during the calculation after. The parking orbit velocity can be calculated using Fish-Vifa equation, which will gives us the parking orbit velocity of 7.73 km per second. We have now arrived on the third part, which is the hyperbolic escape trajectory. The Earth velocity revolving the Sun, which assumed to be circular, can be seen on the top right, which gives us 29.78 km per second. Assuming that the spacecraft will orbit Venus with altitude of 550 km at pericenter and 200,000 km at apocenter, we can find the semi-major axis on the heliocentric orbit. The semi-major axis on the heliocentric orbit can be seen on the left-hand side, which is 128.8 times 10 to the power of 6 km. On the bottom right, we have the illustration of the heliocentric orbit from the Earth into the Venus by the Akatsuki spacecraft. Having the semi-major axis, we can now find the velocity at pericenter of heliocentric orbit, which is 27.27 km per second. Now, we find the escape velocity from the Earth parking orbit to the transfer orbit, which equals to 2.51 km per second, with C3 of 6.3 km square per second square. Analyzing the heliocentric orbit from Earth frame of reference, the orbit becomes hyperbolic, as can be seen on the left bottom side, where the parameters are calculated as follows on the right-hand side, which gives us two important parameters, which is the velocity at pericenter of the hyperbolic orbit, which equals to 11.24 km per second, and the difference of velocity required from parking orbit to hyperbolic trajectory, which equals to 3.51 km per second. It is assumed that during the phase of hyperbolic escape, the change in velocity is provided by the second stage of the H2A202 rocket, the LE5B. Assuming that at the start of this phase, the second stage of the rocket is still in the same as its launch mass, which means has not been used, while the core stage and the SRBA have been released, then the mass at the start of the phase is MO equals to 19,417.6 kg. Using Tsiolkovsky formula, the fuel mass used in this phase is MF equals to 10,806.93 kg, which is still less than the fuel carried by the second stage of the rocket provided in part 1. And after this phase, the second stage of the rocket is released, leaving only the spacecraft. The fourth part, heliocentric trajectory, the transfer orbit. Assuming that the transfer orbit is completed, only half of the full transfer orbit, the time taken is t equals to 1.26 times 10 to the power of 7 seconds, or equals to 145.91 days. With assumption of orbit circular, the Venus velocity revolving the Sun is equals to 35.05 km per second, while the velocity of spacecraft at the apocenter of the transfer orbit is equal to 37.78 km per second. By that calculation, we can find the capture velocity, which equals to 2.73 km per second with C3 of 7.45 km square per second square. On the bottom right, we have the illustration of the heliocentric or transfer orbit of the Akatsuki from the parking orbit of Earth into the Venus orbit. Moving on to the next one, the hyperbolic arrival trajectory, the fifth part. From the previous result, we can find the following parameters which give velocity at pericenter of Venus orbit during hyperbolic capture phase, which equals to 10.29 km per second. Taking Venus as the frame of reference, we can find the following properties. The semi-major axis equals to 106,327 km, while the eccentricity is equals to 0.94. The velocity of spacecraft at the pericenter of Venus orbit will be equals to 9.77 km per second. Therefore, the capture velocity will equals to 0.52 km per second. On the top right side, we have the illustration of the hyperbolic arrival trajectory and the Venus orbit by Akatsuki. Assuming that the propellant left during the hyperbolic arrival state is only the propellant attached to launch mass of the spacecraft, then the propellant mass needed for this state can be calculated. Using Tsiolkovsky formula, the fuel mass used in this phase is equals to mf equals to 110.8 kg. Therefore, there is still 85.5 kg of fuel left to do other maneuver. Last part, the sixth part, which is the comparison between reference data and the recalculated data. The values that can be compared are only the time taken for Akatsuki to reach the orbit of Venus, while the other data cannot be compared as there is no reference data found. The Akatsuki successfully enters the orbit of Venus on 7 December 2015, 5 years after its failed first attempt. However, here the data that will be compared is the recalculated data and the real data of the Akatsuki first attempt. From the calculation, we get that it took 145.91 days of traveling on the heliocentric trajectory or the transfer orbit trajectory, while from the reference data, we get that the Akatsuki was launched on 20 May 2010 on 21:58:22 UTC and initiating orbit insertion on 6 December 2010 at 23:49 UTC, which cost around 202 days. Yes, there is a pretty big difference, around 28% between the calculation and the reference data. But why there is a difference between the reference real data and the recalculated one? I suspect the difference is due to the following. A. There is no calculation for the first part of the flight, which involves the process before the spacecraft reached the circular parking orbit on the Earth. B. The geometry and the altitude of the parking orbit are assumed in the calculation since no reference data found. C. The orbit on Venus is also assumed as there are several different data in the internet about it, which may cause different geometry of the heliocentric or the transfer orbit, although the difference is small. The actual detailed mass of the whole spacecraft during first stage of flight as referred in point A is unknown, as there are several spacecrafts that were also patched into the rocket. E. The time taken calculation is also assumed, which is half period, as the reference data also not found. However, in figure 5 in the reports, we can see that the path shown is more than half period. Again, the data about it is still unclear. And yes, it's a wrap. That is my Venus Climate Orbiter Akatsuki mission reconstruction. My name is Zefan, and see you next time.